Welcome. I'm going to talk about Readiness and Liveness Programming at Kubernetes Ballet Choreography. So this is an exciting topic. I'm thrilled to be here today, and I have the opportunity to share a little bit about myself. My name is Edder Rojas. I'm a full stack developer with a passion for all things tech, travel, and continuous learning. In this presentation, I hope not only share insight and knowledge, but also to inspire curiosity. The topics that I'm covered today is going to be a brief introduction, define liveness and readiness. Before dive deeper into that, why liveness proves, how to serve as a lifeline for our applications, helping us to detect and recover from failure swiftly. Health checks, heard of any robust system lies in comprehensive health monitoring mechanism. Fault tolerance, an ideal world system will never fail. So a brief introduction to that. Determine performance applications with liveness proofs. Beyond just ensuring our applications are up and running, we also want to optimize their performance. And demo. Theory is important, but practical demonstration brings concept to life. In this segment, I'm going to roll out the sleeve and dive deep into some demonstrations, showcasing implementation and benefits of live-proofness in action. Finalizing with conclusions. We're going, as we near end our journey, we reflect on the key insight gaining throughout our discussions. Today, I invite you to explore the delicate dance of readiness and liveness programming set against the backdrop of Kubernetes, the maestro of modern cloud-native architecture. In this captivating performance, we unravel the intricacies of preparing an application for the stage of production, ensure that they are poised and ready for delivery stellar performance at the moment notice. Just a little about the dancer must be both prepared and respond for the demands of the choreography, as application may exhibit both readiness and liveness gracefully to navigate the dynamic landscape of distributed computing. As we delve into the enchanting ballet choreography, we discover the significance each step in the dance. From defining the posture of readiness to the nimble movements of liveness proofs, every element plays a vital role of orchestrating a seamless performance. So sit back, relax, and prepare to be captivated as we embark a journey throughout the enchanting world of readiness and liveness programming in Kubernetes. Together, let's choreograph a symphony of resilience and efficiency that will leave lasting impression on our digital age. Defining readiness. Defining readiness. As readiness proof in Kubernetes is a mechanism used to determine whether a container within a pod is ready to serve traffic. It performs periodic health checks in the container to ascertain if they are initialized properly and is prepared to handle requests. The proof helps Kubernetes manage traffic routing to ensure that only containers are fully initialized and be able to respond for incoming traffic. If it is readiness proof fails from a container, Kubernetes temporarily removes it from the service until the proof indicates that it's ready again. This ensures the stability and reliability of the application running in Kubernetes clusters. If a readiness proof fails for a container in Kubernetes, several actions can occur depending on how Kubernetes cluster is configured. Will be traffic diversion. Kubernetes will stop routing traffic to the container that fails the readiness proof. That ensures only healthy containers receive incoming requests. pod eviction. In this case, Kubernetes might choose to evict that entire pod containing that the container fails the readiness proof. This action is typically taken if the pod is part of a deployment or replica set, and the Kubernetes determines that the pod health is compromised beyond recovery. Rolling updates, if the pod is managed by the Kubernetes controller, such as deployment, Kubernetes may initialize a rolling update to replace the unhealthy pod with a new one. This ensures that the application desired state, as defined, is the controller configuration is maintained. Retry mechanism. This is the more common one. Depending on the configuration of the readiness proof, Kubernetes might retry the proof after a certain amount of time or based on a predefined interval. If the subsequent proof checks succeed, traffic will gradually resume to the container. And finally, logs and monitoring. Kubernetes might log events indicating the failure of the readiness proof, providing visibility into the health status of the container and allowing administrators to troubleshoot and diagnose any issues. Overall, the failure on a readiness proof triggers Kubernetes self-healing mechanism to maintain the desired state of the application, ensure continuous availability and reliability. When defining liveness. A liveness proofs in Kubernetes is a mechanism used to determine whether a container within a pod is still running and operational. It performs periodic health checks on the container to ensure that it is responsive and be able to handle requests. The liveness proof helps Kubernetes detect and recover from situations where the container may have unresponsive or stuck in a fault state, but the container process itself is still running. Similar to readiness proof, a liveness proof can be configured with various types of checks, such as HTTP, TCP, or executing a custom command inside the container. If the liveness proof fails for a container, Kubernetes will take action to remediate the situation, which may include restarting the container or evicting the entire pod if the container repeatedly fails to become healthy. Overall, liveness proofs help Kubernetes maintain the reliability and availability of the application running in the container by ensuring that any issues impacting the responsiveness of container are promptly detected and addressed. If a liveness proof fails for a container in Kubernetes, the Kubernetes control plane will take remedial action based on the post configuration of the cluster policies. Liveness proofs in Kubernetes serves as a crucial role in maintaining the overall health and reliability application running the containers. Here are some key reasons why liveness proofs are important. Automatic restart. Liveness proofs are used to detect if the application inside a container is still running and responsive. If the proof fails, indicating that the application is not functioning correctly, Kubernetes automatically restart the container. Automatic restart can be crucial for recovering from transient failures, temporary glitches, or issues that might cause the application to become unresponsive. Continuous availability. Liveness proofs contributes to the continuous availability of application by regularly checking the health of containers. Kubernetes ensure that only healthy instances are serving traffic. This feature helps maintain a high level of service availability and minimize downtime by proactively replacing containers that are not responding as expected. Fault tolerance. In distributed system and microsystem architecture, components can fail independently, Liveness proofs improve fault tolerance by quickly identifying and replacing failed components, preventing the failure of the one part of the application from affecting the entire system. Self-healing. Kubernetes is designed to be a self-healing system. Liveness proofs contribute to this by enabling Kubernetes to automatically detect and recover from container failures without manual intervention. Self-healing capabilities reduce the operational burden on administrators and enhance the robustness of the entire application infrastructure. Health monitoring. Liveness proofs also serve as a form of health monitoring for our application. They provide insights into the runtime behavior of the application and help diagnose any issue by indicating when the container became unhealthy. Monitoring the liveness status over the time can be valuable for analyzing the trends and identify patterns related to stability and reliability of the application. In summary, liveness proofs in Kubernetes played a crucial role in ensuring that continuous availability, fault tolerance, and self-healing capabilities of the application by automatically restarting the containers that exhibit issues. Kubernetes helps maintain a resilient and reliable infrastructure for running distributed applications. Health checks. Health checks includes liveness and readiness proofs in Kubernetes are essential for maintaining the reliability and ability and performance of the applications. Here is several reasons why health checks or health monitoring is in general are crucial. Proactive issue detection. Health checks allow the proactive detection of issues within an application or its components by regularly assessing the health of different parts of the system. Potential problems can be identified early before they escalate into critical failures. Automatic recovery. By enable automatic recovery mechanism in system when automated health monitoring on healthy components can be automatically restarted or replaced, minimizing downtime and ensuring that the overall application remains operational. Continuous availability. Health checks contribute continuous availability by ensuring that only healthy instances receive traffic. In a container orchestration system like Kubernetes, unhealthy pods can be temporarily removed from the service, preventing from negatively impacting the user experience. Preventing resource exhaustion. Health checks can help prevent the resource exhaustion by monitoring the health of application that system can avoid direct traffic to instances that might be struggling due to high resource utilization, preventing a cascade of failures. Gracefully scaling. Health checks plays a crucial role in determining when a new instance can be added to a deployment. Readiness proof, in particular, ensure that newly started container is ready to handle traffic before it includes into the load balancing pool. Predictive maintenance. Regular health monitoring can provide a data for predictive maintenance by analyzing historical health checks results. Administrator can identify trends that may indicate potential issues before the impact of the system performance. In conclusion, health checks are critical for ensuring the stability and reliability of the application by enabling proactive issue detection, automatic recovery, and optimized resource utilization. They are foundational for modern system architecture, particularly in containerized orchestration environment like Kubernetes. Determine performing application with liveness proof. In this context, to determine the performing application, these topics are crucial consideration assessing the overall health and often in the underlying structure. Liveness proofs can be configured to monitor those aspects and trigger action to maintain optimal performance. With part startup refers the ability to an application to initialize by becoming operational quickly after being deployed or restarted. Application with fast startup times reduce downtime and improve responsiveness, especially in scenarios when containers are need to scale and recover quickly. Effective resource utilization involves optimizing the consumption of CPU, memory, storage, and network resources by the application. It ensures that the resources are just not a waste of maintaining high performance without causing contagion or bottlenecks. Granular, granular health checks involve breaking down the health monitoring on application into specific components or functionalities. Instead of just checking if the application as a whole is healthy, granular health checks assess the health of the individual services, endpoints, or critical operation within the application. Concurrency and scalability. Concurrency refers to the ability of application to handle multiple tasks or requests simultaneously. Scalability is, on the other hand, refers to the application ability to accommodate increasing workloads by adding more resources or instances. Applications should be designed to handle concurrency requests effectively and scaling horizontally to meet growing demands while maintaining performance. Caching strategies involve storing frequent access or computational expensive data in memory or a fast access storage layer to reduce responsive times and improve performance. Connection handling. Connection handling pertains to how the application manages incoming requests, establish connection, and process data from clients or other services. Monitoring and metrics involves continuous collection, analysis, and visualizing key performance indicators, KPI, as a metric related for application health, performance, and resource utilization. Monitoring tools and dashboard provide insights into the system behavior, identifying performance bottlenecks, and help diagnose issues proactively. And finally, graceful degradation refers for the ability of the application to maintain essential functionalities and service when the experience downgraded performance is encountered failures. Instead of failing completely, the application gracefully adjusts its behavior or reduce its features to ensure critical operation remaining available for the users. Here we have a brief explanation. In this straightforward demo, I am to show you how readiness and liveness proofs are configured and how they behave in Kubernetes. I'm using a Kubernetes cluster locally via K3D for my environment. This cluster will host two distinct applications, serving as a demonstration for readiness and liveness proofs. Here we have one of the applications configured with a ready endpoint, which is utilized by the proof to ascertain if the application is ready and accepting connections. The process of building and deploying the application is as follows: build through Docker. The Docker file is a multi-step file that copy, fetch, and install dependencies and leave the main process running at the end. Then we need to import the image in K3D. Since K3D tries to pull the image from the registry, an import is needed. So we need to import the image
into the cluster to be available. Then there is a deployment configuration file, which is we need to make the configuration that uses the namespace for this demo, and this deployment that uses the local image with the image pool policy to never to, instead of going through the registry, use the local image. And finally, we have the readiness proof, which is points to the Redis endpoint with a period that will execute every 5 seconds, and it will start doing the proofs every 5 seconds, or the initial delay of 5 seconds. Then we have the service, which is going to allow the port to be accessible. For the liveness application, which is as follows, we have the same configuration from the Docker file and the step to build in and include an image. The only difference is that at the service level, we have different image, and we include environment variables for fetching the service. We also have a readiness proofs, which is going to return an OK with a period every 3 seconds and an initial delay of 5 seconds as the other application. And the liveness proof will point to different endpoint, which is going to perform health checks by trying to reach out the other service with an initial delay of 10 seconds to avoid collisions, and with that readiness proof. Every 3 seconds is going to be executed. After 3 times, it will try to restart. Each restart will have a grace period of 60 seconds, so I will terminate that container. That service will be the same definition to allow the port to be accessible. So let me open, let me show you the cluster on OpenLens. In OpenLens, we have these 2 deployments, which is the services that I explained before. Currently, there's no pods running. So let me start the other service first, which have the readiness proof configured by scaling up 1, and wait a few seconds to demonstrate the service is starting. Once it's started, it will start performing the readiness proofs, which is, I think we have the 5 seconds already, which is shows us a screen. Now we have these events and this pod running. Let me start the other service. Let me scale up this service to 1 and monitor this container. Here you can see the liveness and readiness configuration already defined. And let's wait a few seconds to display the events. Since everything seems to be fine and we have reached more than enough for the liveness to be executed, everything seems to be fine. So let me scale down the other service to display what will happen if the liveness doesn't respond or the liveness proof fails. Now we have this container that is terminating. And let's wait for the liveness proof to start throwing events. Now that the container is done, now we get errors on the liveness, and the container will restart after a few seconds. Now we reach the count. We'll start improving. Then we have the first restart. That will happen for a while until the service is up and running. So let me get back online again. Now the container is started. You can see that the container is still trying to determine if the liveness probe is ready. And once that happens, we will mark as green. That's basically the demonstration. Thank you.
In conclusion, the journey throughout the readiness and liveness proofs in Kubernetes has provided us with invaluable insights into the orchestration of the resilient and reliable containerized applications. Through the lens of readiness proofs, we've learned how Kubernetes ensures that only fully initialized and prepared containers receive traffic, optimizing the stability and performance of our applications. By configuring meaningful proofs and monitoring their results, we can effectively manage traffic routing and enhance the overall user experience. Similarly, our exploration of liveness proofs has underscored the crucial role in detecting and recovering from container failures. Kubernetes' ability to continually assess the health and responsiveness of containerized on containers enable rapid remediation actions, such as restarting the containers or evicting pods to maintain application availability and uptime. As we navigate the dynamic landscape of cloud-native architecture, Readiness and Liveness proofs serves as our steady, fast companions, guiding us towards resilience and efficiency. By embracing these mechanisms and incorporating best practices into our workflow, we empower ourselves to build robust, scalable, and fault tolerance applications that meet the demands of modern digital environments. Thank you for joining on the journey of Readiness and Liveness Programming in Kubernetes. My future endeavors that guided by the principle of reliability, agility, and continuous improvement. Together, let's continue to innovate and elevate the standard of cloud native computing. If you want to learn more about this topic, you can review this link through the QR code or visit Veritas Automata.com website. Thanks again for joining. My name is Edder Rojas. My LinkedIn information is in the QR code. Looking forward to connecting with us.